This is Mike Ritz, W7VO, and today we're going to talk about HF noise mitigation, kind of a magical thing to talk about. Let's go ahead and get started. So what will you learn today? Well, the first thing we're going to do is talk all about noise, kind of finding out what noise is. Then we're going to talk about noise mitigation itself, followed by how to characterize your RFI environment to kind of find out where the noise is coming from. And by the way, what we'll have time to discuss today is just the tip of the iceberg. This is a really complex subject, and we really only have about 25 minutes to do it. So let's go ahead and get started. So what is noise, right? What is this magic stuff called noise? Well, in radio terms, noise is an unwanted signal from sources other than a transmitted signal source that falls within the passband of the receiver. In other words, it's not intelligent. It does not convey any information. It's of random frequency, amplitude, and pattern. And noise can either be internal or external. In other words, internally generated or externally generated. And internal, it's described as being generated within the radio itself. Every electronic component in a radio will generate noise. Amplifiers amplify noise as well as the signal. So tubes generate a lot of noise with harmonic emission. Transistors generate noise, even resistors generate noise. And external is from an external source outside of the radio. So I talk about the receiver passband. So what is the passband of the receiver? The passband of the receiver is what contains all the information. So when you tune a radio around, what you're really doing is moving this little window around. This window is where you receive the signal. And if a noise source or interference source falls outside this passband, it's really not of much concern. It's only when it moves into the passband that it really becomes a problem and something that we have to try to figure out how to mitigate. Let's talk about broadband versus narrowband noise just for a second. In the narrowband noise situation, it could be within the passband of the receiver. If it's not within the passband of the receiver, it's not really noise. But it could also be what's called wideband noise. And a wideband noise, it's not only within the passband of the receiver, but it extends well beyond that. Sometimes kilohertz, sometimes megahertz, sometimes multiple megahertz in width. It's really much harder to mitigate it when it's extremely broadband. So let's talk about noise versus interference. Noise is not to be really confused with the term interference. And interference is defined as when information signals from one source produce frequencies that fall outside their allocated bandwidth. In other words, they're not where they're supposed to be, and interfere with signals you want within a passband receiver. And we've all run into these on the air. Examples are splatter, really wide signals on single sideband, CW key clicks when you have CW signals with really fast rise times, and of course harmonic interference when you've got a signal that perhaps starts out on 40 meters, but you can also hear that same signal on its second harmonic, which may fall within the 20-meter band. There's also different types of noise. There's natural noise, noise from our sun, atmospheric noise, our own atmosphere creates noise, and also extraterrestrial noise that occurs from beyond our solar system. And of course, the bane of our existence here, man-made or industrial noise. We're going to talk a little bit about that. Some types of noise we can control. For example, if you've got an arcing insulator on a transmission line, you can call your local power company and hopefully they'll come out and fix it for you. But really, sometimes there are some noise sources that you can't really control. For example, a barking dog in the middle of the night. Let's talk a little bit about solar or cosmic noise. The sun is basically a great big giant fireball in the sky, right? Thermonuclear explosions over and over again. And it's also a huge wideband RF source, basically emits from DC to light. There are three components of solar noise that all kind of get different types of radio waves. There's the background noise, which is the normal noise the sun generates. And a lot of that is to do to the fact that it operates at 6,000 degrees Kelvin. There's also what's called the slowly varying component, differing temperature areas of the sun, for example, sunspots, which are a cooler area of the sun, but are very active in magnetic activity. And the burst component that we're all too familiar with here, coronal mass ejections, also known as CMEs, and also solar flares that can wreak havoc with our propagation. And of course, extraterrestrial. That's not only is our sun out there generating noise, but there are billions and billions and billions, as Carl Sagan would say, of noise sources in other galaxies and from lands far away. So if you take a look at the sun's electromagnetic spectrum, you can see that there's about 49% of the energy produced by the sun in radiation intensity is from the AM radio waves, basically around a megahertz or so, all the way up to the near infrared. And as it gets higher and higher in frequency, it generates more and more intensity. And about half of the sun's output in radiation is basically radio waves. Let's talk a little bit about natural noise. We have atmospheric noise, thermal noise from the atmosphere. The sun's beating on the atmosphere and causing heat. That heat generates thermal noise. By far the largest noise source on our planet is lightning. There are about 3.5 million lightning hits per day, 7 days a week, 365 days a year. So it by far is the largest single noise source that we have on Earth to deal with. And there's also smaller versions of this. You may have heard of snow static, and that's when a snowflake comes down, or a clump of snowflakes come down. They pick up an electrostatic charge on their way down to the ground and stop at your antenna on the way and discharge the static onto your antenna, which could wind up being a very high noise floor on your radio. I've had this happen during contests sometimes in the winter. And keep in mind that most natural noise is mostly random frequency and random polarization. So that makes it pretty hard to mitigate, but there are some ways that we can do that, but it is harder. Keep in mind also that atmospheric noise, and this is an interesting thing to think about, the field strength of atmospheric noise varies approximately inversely with the frequency. The higher the frequency, the lower the atmospheric noise. And there's a couple of reasons for that. Most atmospheric noise is generated in the low and medium frequency bands, and there's very little noise generated on the upper bands, on VHF and UHF and into microwave. And there's also another thing that's interesting about the noise that is generated up there is that primarily, as we all know, VHF and UHF signals are basically line of sight. So there is noise propagation on the medium frequency and low frequency, just like there are for radio waves. It also noise propagates around the world the same way. Well, in the VHF and UHF spectrum, of course, it's line of sight, which really limits the amount of damage that noise can do. Let's talk a little bit about man-made noise, also known as RFI, or radio frequency interference. There's noise internal to the radio itself, right? This is a man-made noise. Thermonic emission in vacuum tubes, transistors generate noise, amplifiers, by their very existence, not only amplify noise, but they generate noise themselves. SDR radios, by the way, suffer much less from this problem. The reason is there's a lot less electronics in there. Software doesn't make much noise. But the analog radios do. So SDR radios are basically just A to D converters, and then some magic in software, and then a D to A converter at the end that turns it into sound. And there's not a lot of electronics, so they're a lot quieter. Switching power supplies generate a lot of RFI. The big heavy ones that have transformers in them that are analog based work very well. The bad ones are the little light ones that are switching power supplies. But really on all these little wall warts, if you can, eliminate them altogether and use one single low noise supply, or even better yet, a battery system. There are computers. Computers themselves, this laptop, we're going to see just how noisy it is in a little while. I've got a graphic for that, but computers generate a lot of RF hash. Plasma televisions, right? Everybody remember when plasma televisions came out, they were extremely noisy. Street lights, modern LED street lights are pretty noisy. The old sodium vapor lights were pretty noisy too. Fluorescent lights and ballasts, right? They're heating up that plasma, generates some RFI. Solid state light ballasts are a problem. They're basically switching power supplies versus the old analog ballasts that had transformers in them. And of course, power line noise, one that we're all too familiar with. And the modern thing now that's coming up in a lot of hams neighborhoods are LEDs and grow lights. And cannabis growing is legal here in Oregon, and they've really been a huge problem, especially for some of the hams that live down in the southern area of the state where they do a lot of cannabis growing. And if you get a good cannabis grow operation with you know, a couple of hundred of these 2,000 watt grow lights that are not FCC type accepted, can generate a lot of noise for miles and miles and miles. And keep in mind that most man-made noise is vertically polarized, at least in the near field, right, till it bounces off of something. And that makes it a little bit easier for us to mitigate the noise. And most of these man-made noise sources are things we can control because they're, you know, they have a common polarization and other things. And really, it's all about going after the source if you can. But sometimes you can't. You can't really go after the source. If you can't, what do? Well, we do what we can do. We mitigate. So now we're going to go on to section number 2. Okay, now we're going to shift gears a little bit and talk about noise mitigation, right? What can we do to eliminate the noise? Well, to eliminate noise, it's really all about the signal to noise ratio. You either have to increase the level of the signal or decrease the level of the noise. It all comes down to a simple math equation. But really, there is no magic bullet, right? There's not one thing that you can do to completely eliminate noise, but there are a lot of ways that we can work to mitigate it. But my radio has a noise blanker, a little control right here. It's a little knob that says noise blanker, a little button. And boy, that should be able to get rid of all the noise, right? Well, not quite, because these radio noise blankers really work best on impulse type noise, like spark plugs or spark plug wires that are leaky, or fence chargers that are used to contain animals in a barn or in a pasture setting. These things really don't work on the wide variety of man-made noise, and especially on atmospheric noise, but there are some things that we can do, but noise blanker, unfortunately, is not the answer. So how do we mitigate received noise? Well, we start by working on the antennas, right? Verticals, if you've got a vertical antenna, verticals are inherently noisy. Remember that the man-made noise is primarily vertically polarized, and by having a vertical antenna, you're essentially matching that up with the vertical polarity of the noise. So verticals are inherently noisy. However, Yagis are less noisy. It's a combination of the fact that they're horizontal polarization, and they're also directional. So you can not only get a louder signal, right? It's all about increasing the level of the signal. You can also decrease the level of noise by steering the antenna away from noise sources. Also, make sure you have proper bonding and grounding of your equipment. There's a book you can get for that, and really to avoid having noise come into your station via common mode on the outside of the coax, make sure that everything is properly bonded and grounded. Use ferrites. I use an awful lot of ferrites on my station. I've got them on just about everything, including all the coaxial feeds that come in right before they come into the shack. Jim Brown, K9YC, has technical information on this. You'll see a slide at the end that tells you how to get a hold of his wonderful website and publications that he has for free about ferrites. And if you do buy ferrites, make sure that they're type 31 material, which has the correct permeability for the frequency range we use on HF. And learn how to use the controls on your radio. A lot of people go out and buy a new radio, and they'll plug it in, they'll turn it on, they'll use the volume control, and they'll use the frequency, VFO control, and that's all they learn how to use. And there's really a lot more that these modern radios have, and if we know how to use those, read the manual, you'll understand better how to help mitigate noise. If you can, move your antennas away from noise sources. If you've got one that's very close to a power line, try moving it away from the power line. If you've got it right by your house, try moving it away from the house. That's always not feasible. And as a last resort, we can try using what's called a noise canceller device. And we're going to be talking about those in detail here in a few minutes. So noise mitigation, get to know your radio, right? Get to know what all those knobs do. A lot of radios have RF gain controls, and we typically run those 100% full on. and we use the volume control to adjust the volume. I'm going to suggest to you that you may want to set the volume at a certain level that's comfortable to you, and then use the RF gain as a volume control. You'll find out, especially in noisy situations, you can actually, by turning the RF gain down, you can actually bring a signal out of the noise. If your radio has preamplifiers, switch settings, leave them turned off, except maybe on 10 meters or 15 meters, or maybe on 20 meters if it's a very quiet atmospheric time. But on 40 to 160 meters, leave those preamps turned off. When you leave them on, is all you're doing is amplifying the noise and the signal, and you wind up with really much worse off than you started off being. A lot of modern radios have attenuators that you can switch in on. You want to especially use those on the low bands, 80 to 160 meters. And the purpose of that is to keep the noise from overloading the receiver AGC. I use between 6 to 20 dB as needed. And you'll be surprised, you'll turn the attenuator on, all of a sudden the signal will rise up out of the noise on 80 meters. If you've got a radio that has IF filtering in it, think about maybe narrowing it down a little bit. You know, they have 500 hertz CW filters, 250 hertz CW filters. If you don't have any filtering at all, add them. You know, figure out where you can get them and add them. Even old tube radios, you can buy the filters online on eBay and other places. Know how to use the IF passband or IF shift control on your radio, and we're going to talk about that in a couple of minutes. And if your radio is a modern SDR type radio, especially if it's got digital signal processing built in, learn how to use them. You know, there's a lot of controls there that'll help you with mitigating noise. Here's an example. Here's a Yaesu radio, and it's got a variable preselector knob. It's got one to adjust the passband IF width. You can actually shift the IF width back and forth. An IF notch filter, a digital noise reduction control that's always useful, and a contour button that's used to shape the receive signal. So, I mean, there are lots of knobs, and you know, look in your manual and figure out how to use these things, and they'll really help you in noise mitigation. Here's an example of one. This is from an ICOM manual, but it's a passband tuning knob that you can control. And here's the knob down here. And so what they did is they're showing the passband is within this where it says desired signal, and they've got a little signal here that's they're receiving, and they've got an interfering signal that's right within that passband. And what they do is that by turning the knob to the left, you can actually shift the passband over. The signals stay where they were, but now you've completely eliminated the interference signal. So once again, you've gotten rid of the noise just by turning one little knob. And I use my IF shift knob on my Yaesu radio quite often, probably as much as I do the volume control. There's also special antennas you can get that'll help you with noise mitigation if you've got the room for them. I have a beverage antenna that's about 400 feet long that I use on the low bands. You can also, you know, build your own K9AY type loop antennas. You can also use a receive loop to help null out noise. There's lots of different antennas. There's lots of literature you can get on these. They really do help on, especially on 80 and 160 meters. As a last resort, consider using an external noise canceller. And there's several of these on the market out there. There's the MFJ 1025 and 1026. The JPS Time Wave ANC4, the one in the middle here, and DX Engineering has a couple of different models, the NCC1 and NCC2, and there may be others out there as well, but these are probably the most popular ones that are used. So how do these magic boxes work? Well, remember, it's all about the signal to noise ratio. If we can cancel out the noise, all that's left is the signal. These noise cancelers, you have a separate antenna input for a low gain noise antenna, and its job is to only pick up the noise, not the signal. So it's really a pretty crummy antenna. It's not something you'd want to use for making QSOs, but what we're trying to do is only pick up local noise, whether it be from a power pole, whether it be from something within your house or your neighbor's house. We want to get the noise only, not the signal. And I have a couple of these antennas. One of them is a very low fence mounted vertical that's mounted close to a power pole. I've got some power line noise here. And I've also got a very steep inverted V. Basically, it's an old 40-meter antenna off my main tower that is basically just runs along the length of the tower going down. And it picks up, gets coupled noise from the tower. If the tower picks up any common mode noise, I can bring that into the shack and cancel it out in my noise canceller. Loops work very well too. You can use a loop to null out the signal so you only receive the noise. And where these cancelers install is between the radio and the antenna, or the radio and the tuner or amplifier. They have built-in TR switching, good up to 100 watts. They automatically detect when you're transmitting, and they switch themselves out of the circuit. If your radio has an external receive antenna input port, you can actually connect it there, and it works quite well. You just push the receive antenna port, and all of a sudden now the noise canceller is in the line, and you're in business. Here's kind of a little schematic diagram of how they work. Basically, your main antenna, which would be a Yagi or whatever you've got, is picking up both the signal and the noise. But you have your low noise gain antenna, which is only picking up the noise, goes through a phase inverter. It's mixed with the signal plus the noise. And because these two cancel out, the only thing technically you've got left over is the signal. These work best on noise that has a consistent pattern, for example, man-made noise. But I've also had them work on atmospheric noise as well. They just don't work as well. And note that both the phase and the amplitude of the noise on both antenna ports must match in order to cancel out the noise. They've got to be the same. So that's why all of these devices have controls on them. So they're really kind of fiddly, right? You just don't flip a switch and all of a sudden it's there. You've got to actually spend some time and get everything to match up. But if you're trying to get that rare DX station or that special multiplier in a contest that, and you can just barely hear them, this might make the difference between making a QSO and not. But I mean, it's something that you've really got to play with in order to get them to work properly. So this will be the end of the first section. We'll move on to part 3 now, characterizing your noise environment. A little quick overview. We know we have noise or RFI at our shack, but what does it really look like? And I've often used just a cheap little AM radio to walk around and try to find noise sources. You people that may have seen some of my live presentations, I actually have a demonstration where I have a radio and I can actually listen to noise. But it's a lot better if you can actually see it. So in order to see it, you have to visualize it. And in order to visualize it, you need a different perspective than a typical HF radio will offer. And so you're going to say, well, wait a second, my radio's got a pan adapter. That should work just fine. But pan adapters really only look at a very small slice of the spectrum, and usually only after filtering. So they've got the front end filtering, and then they pick the pan adapter picks off in the IF, and doesn't really give you a full picture of what's going on. So pan adapters work, but don't work as well. So what does it take to actually see and not just hear RFI? Well, it takes a software-defined radio, or SDR, plus a computer, laptop computer works just fine, and some software. An SDR, it basically uses a computer to replace the electronics of the radio, or it is a radio, but it's strictly software. So all signal formatting is done mathematically in this thing. It's really kind of on the front end of an SDR is an analog to digital converter, and then there's the magic software, and then at the other end is a digital to analog converter, and converts it back into sound again. And so basically all the electronics, or all the radio conversion and IF is all done within software, which is, by the way, a heck of a lot less noisy than a typical analog radio. As such, SDRs do not suffer as much from internally generated noise. If you turn a volume control up on like an old FT1000 radio, you can as soon as you turn the radio on, you start hearing noise right away before you've even got a antenna connected to it. Do that on a modern SDR radio, and you can turn the volume control up as far as you want to go, and you'll barely hear anything as far as noise is concerned. They are so much quieter than older radios. So to set up an SDR, if you buy one, make sure it covers the frequency range you're interested in. If you get one of the little cheap dongle radios, make sure it covers the HF band. A lot of the cheaper ones will start at maybe 30 megahertz. You want to download and install the software and the drivers. You want to connect the radio to either your antenna, your outside antenna, if you're trying to pick up noise in your neighborhood, or you can also use a small loop antenna in order to pick up local noise within your shack or within your house. You can add a broadcast filter if necessary. If you've got a local AM station that's close to you, you may want to pick up one of these accessory filters. I use a software package called SDR Sharp. It's free. It's pretty powerful. And I use a very cheap RTLSDR.com USB dongle as the radio. It's like 30 bucks or less on eBay, but there are many others you can use. You can spend, hundreds of dollars. You can spend a few dollars. So let's take a look at some screenshots. And what I have here, first of all, this is Dave NK7Z down in Eugene, Oregon, is a technical resource RFI expert here in the ARRL Northwestern Division. And he had a grow operation for cannabis that popped up down in his neck of the woods down there. And he started finding 40 meters was basically unusable. And if you take a look at here, he actually took a screenshot of noise at his station. And here's 40 meters. This is at about 7005 here, and goes up to about 7160. And look at all this noise in here. And there's also another patch that starts at about 6960 and goes back. And this is all noise from the LED lights at the grow operation. It basically makes 40 meters unusable for him. He can also visualize RFI over time. And here he's taken where this thing takes a snapshot every 15 minutes or so. And you can see all of a sudden he had all this noise. It changes frequency. It changes amplitude over time. You can see as it drifts around here a little bit. And you can see that all of a sudden at a certain time, the lights turn off. And what happened was this grow operation had the lights on all night. And when it became day, they turned the lights off. And all of a sudden, look at all of a sudden now, he's starting to receive signals he didn't receive before because the grow operation. So, I mean, you can use this thing, you can also document if you do have RFI problems that are coming from someplace that's beyond FCC limits, and you have to have some kind of proof for the FCC by taking these screenshots. It might help you in some future litigation as far as getting them to clean up their act. Here's what I use at home. I use a very crude loop antenna. It's basically a steel coat hanger that's unwrapped and connected to an SO239 connector with some coax. I've got a little ferrite core here that I can use to keep the common mode noise out of the RTL dongle. And this is the dongle that I use. This is basically USB, plugs right into the laptop, and it's got a little SMA connector that connects to the loop. And I can actually walk around my house with the laptop and look at the various noise that are being created by stuff within my house. This is actually a screenshot of my RTL with the loop and using the SDR Sharp software. And this is actually sitting in my office at home. And you can see I've got some noise sources in here. I've got a little bump here and one here that kind of changes it kind of goes on and off. You can see where it gets turned off and back on again and off and on. And here's one that stays pretty constant. There's another one down here, and this happens to be on the 10 meter band. My dongle only goes down to about 24, 25 megahertz. So I can only look at the 10 meter band and going up. And then here's, this is when I start getting the loop close to my Hewlett-Packard printer. You can start seeing now all these noise sparks, noise peaks that pop up all of a sudden. And you can change, if you go around various, aim at various ways around the printer, you can get different readings and different amplitudes. You can kind of find out where the noise source exactly is. Here's another one here. If I get too close to my Dell laptop, look at how the noise floor now, talk about wideband noise. Well, here's wideband noise. And you can see that just getting within about 2 feet of my laptop, the noise floor has increased probably 20 or 30 dB. And so you would not want to have this computer next to a radio that might be sensitive to it. So it's just, you can use these as a great tool to go around your house and try to track down noise sources. Here's some resources we have available for you. I mentioned we'd have them. Jim Brown, K9YC, has a free publication he offers on his website called RFI Ferrites and Common Mode Chokes for Hams. Excellent publication. Dave Cole, NK7Z, is our ARRL Northwestern Division RFI technical resource. He's an assistant director for us here in the division. He's got his own website, nk7z.com. radio.net. You can also, of course, get the ARRL book on grounding and bonding for the radio amateur by Ward Silver, N0AX, and the RFI's also got, or the ARRL also has an RFI book you can buy and an RFI web page on their website. And with that, we're going to close it out and say 7 3s. And thank you very much for allowing me to present here today. I want to thank Eric and the team at QSO Today. And now we'll take some Q&A. So 7 3.